Welcome back to the deep dive. Today we are focusing on a component that's so universally used in modern construction,
Yeah.
yet so specialized that if you pick the wrong one, your entire wall will, well, it will eventually betray you.
It really will.
We're talking about the drywall screw. And this is not just a piece of hardware. It's a masterclass in engineered optimization.
That's absolutely the mindset we need to approach this with. Our mission today is to look at the anatomy of this seemingly simple screw and dissect precisely why its shape, its threads, and even its, incredibly specific internal metallurgy,
Right.
down to the use of boron, are completely non-negotiable for achieving a flawless, stable wall finish that meets modern European standards. We are looking way beyond the surface level of function and diving into the chemical and mechanical engineering required.
And we have a fantastic roadmap for this deep dive. Our source material gives us a real technical blueprint, charting the specialized demands of the European fastener market. We have deep analyses comparing the wire rod materials C2 and O22 and C10B21. We've got details on essential coatings like black phosphate. And crucially, we're dissecting the rigorous compliance standards that dictate performance, specifically EN 14566.
And the goal isn't just to, list these facts, but to show you how they all connect. We want you, the listener, to be able to pick up a drywall screw, recognize its specific design features, the head, the thread pitch, the color, and instantly know its intended substrate, its material composition, and the exact compliance framework it operates under.
Okay, let's unpack this by starting at the top. The massive industrial ecosystem that demands this level of specialization. I think before you can really appreciate the hyper-focus of the drywall screw, you need to understand the vast playing field of the European fastener market.
It is a colossal sector, absolutely, and its scale dictates innovation and specialization. To give you an idea, the European industrial fasteners market was valued at approximately, $23 billion in 2024.
23 billion.
Yeah. And that figure isn't static. It's driven by relentless growth in construction, infrastructure, and, critically, the huge and consistent demand from the home renovation and DIY sector.
Right.
When you have a market that large, you just can't afford to use a one-size-fits-all fastener. Each application demands a tailored solution, and mass production allows for that level of specificity.
And within that DIY sector, there is one absolute champion, a real workhorse that defines the bulk of European home assembly and workshop projects.
Oh, for sure.
And that's the chipboard screw. We have to understand this one first because it perfectly illustrates the engineering principles for dense wood composites, and that really sets the stage for the drywall screw's necessary divergence.
Precisely. The chipboard screw is fundamentally tied to European culture, specifically the massive success of flat pack and ready-to-assemble furniture.
You mean all the big furniture retailers?
Yeah, exactly. Think of those big blue and yellow stores. Every single one of those assembly manuals relies on the chipboard screw. Its primary use case is joining engineered wood composites particle board, chipboard, and medium-density fiberboard, or MDF, which are really the cornerstones of affordable cabinet making and internal structures.
So if I am designing a fastener specifically for dense, but I guess essentially fibrous and somewhat fragile engineered wood, what are the non-negotiable design characteristics? What makes a standard wood screw fail where a chipboard screw excels?
It really comes down to threads and material handling. MDF and chipboard, they're prone to swelling, and they don't hold threads well if the screw is too aggressive or, too smooth.
Right.
So if you look at the specific design features of a successful chipboard screw, the threads are the first thing that stand out. They're deep and coarse.
Deep and coarse. Okay, why? What does that do?
Well, the depth is crucial because the material itself, that composite of wood fibers and resin, is relatively soft compared to solid hardwood, but it's also very densely packed. The deep thread profile is designed to cut efficiently through this dense fibrous medium. It ensures maximum thread engagement, meaning more surface area of the screw is gripping the board, and it minimizes the risk of the screws stripping out the hole during insertion.
Which is a huge problem with particle board.
It's the most common failure mode, yeah. And the coarse pitch that provides the aggressive bite necessary for high holding power, preventing the screw from backing out under the constant minor stresses inherent in furniture assemblies.
And the head design serves a specific function for furniture aesthetics, right? It's not just about torque transfer.
Absolutely. I mean, while they require good torque transfer, they are primarily focused on the finish. Chipboard screws almost always feature a countersunk head, or sometimes a pan head for specific load distribution. But the key functional refinement is the use of specialized features underneath the head, often called nibs.
Nibs. You mean those tiny little ridges or serrations you sometimes see?
Exactly. Those nicks, they act as a built-in mechanical countersinking device. As the screw head meets the surface of the chipboard, these ridges engage and they ream out a precise, small space, allowing the screw head to sit perfectly flush with the material surface.
So you don't need a separate tool.
You don't. It means the installer doesn't need a separate countersink tool to achieve a clean, professional appearance. This efficiency is paramount in high-volume, flat-pack assembly, where speed and finish quality are, key performance indicators.
And the material selection for these screws is also highly specific to their environment. We're talking dry indoor use.
Correct. Chipboard screws are typically manufactured from hardened carbon steel. And because they're destined for furniture or dry interior spaces, they are most often zinc-plated. Sometimes it's called BZP, bright zinc-plated.
And that's really an economical choice.
It is. This zinc provides a mild, sacrificial corrosion resistance. It's adequate for a climate-controlled room, but it's definitely not designed to handle high moisture or external exposure. This is an important detail, as the volume and price sensitivity of the furniture market means every manufacturing choice, from the inexpensive BZP coating to the use of C2122 steel wire rod, which we'll get into later, is optimized for cost efficiency and its very narrow, defined environment.
So, to summarize where we are, the chipboard screw is a master of its medium. It's got deep threads for grip in dense composites, nibs for a perfect flush finish, and cost-effective mild corrosion protection. It's built for strength and stability in fibrous wood materials.
Which brings us perfectly to the transition. The chipboard screw is optimized for stability in dense material. The drywall screw, however, is optimized for speed, precision, and critically minimizing damage in the most fragile, brittle material possible, gypsum plasterboard.
Right.
The design priorities completely flip. Instead of aggressive bite into dense fibers, the drywall screw requires finesse to pierce thin paper without tearing it.
Okay, so this is where the specialization really takes over. You mentioned finesse. When you hold a drywall screw, the first thing that strikes you is its unique curved head. This geometry, it almost looks like it was designed by a sculptor, not an engineer. This is the definition of targeted specialization.
It is precision engineering applied to material science limitations. Drywall screws, or plasterboard screws, as they're also called, have one single job.
Yeah.
Attach gypsum boards securely to studs, whether they're wood or light gauge steel. And crucially, they have to do this without compromising the board's paper surface, which is essential for holding the jointing compound.
And in the European construction context, this isn't just about what looks nice or what works best. It's heavily standardized.
Oh, absolutely. In the EU, construction materials must adhere to strict performance and safety criteria. Drywall fasteners have to comply with BS EN 14566.
EN 14566.
That's the one. It's the standard that defines the mechanical fasteners for gypsum plasterboard systems. It dictates everything from minimum dimensions or materials to required test methods, ensuring the screw contributes to the overall stability and, critically, the fire rating of the finished wall system.
Okay, let's dedicate some serious time to that bugle head design.
Yeah.
Because this is the finishing masterpiece that truly separates it from all other fasteners. Why the smooth curve? And why would using a standard countersunk screw on drywall be a complete disaster?
Well, the standard countersunk screw, like the one you'd find on a chipboard screw, has a sharp angled underside.
Right, like a cone.
Exactly. If you drive that into soft gypsum board, that sharp edge acts like a little knife. It will instantly slice and tear the thin paper facing of the drywall.
And the paper is everything.
The paper is where all the screw's long-term holding power resides. Once you rip that paper, the screw is only held by the crumbly gypsum core, and it will eventually fail. It will pop out or loosen when the wall flexes.
So the paper layers is actually the structural anchor.
It is the membrane that transfers the load from the screw to the wallboard. The bugle head, by contrast, is designed with a continuously smooth parabolic curve. When it's driven, instead of cutting, this curve gently compresses the soft gypsum material and presses the screw head just slightly below the paper surface.
Ah, so it creates a little dimple.
It creates a perfect, shallow dimple without tearing the crucial paper face.
A controlled compression instead of a catastrophic cut.
Exactly right. This dimple is shallow enough to be easily filled with jointing compound, the plaster product used to cover the fastener heads and seams, creating a perfectly level surface that can be sanded and painted over, making the fastener completely invisible.
That flawless aesthetic finish is completely dependent on the bugle head design.
100%.
That makes perfect sense. Now let's move from the head down to the body. We saw that the chipboard screw is optimized for one medium, wood composite. But the drywall screw has to handle two completely different structural materials, wood studs and thin steel studs. And this requires two distinct thread designs.
This is where the specialization really becomes evident. You absolutely need to identify your substrate before you pick your screw.
Okay, let's start with the coarse thread. This is the familiar one, right? The one typically paired with that black phosphate finish we'll discuss later.
That's the one. The coarse thread drywall screw features a deep, widely spaced thread pitch. This design is optimized for grip and speed in the fibrous, resilient structure of wood studs.
So it's for wood.
Yes. The coarse thread cuts deeply into the wood fibers, maximizing pull-out resistance. And importantly, most modern coarse thread screws also utilize double lead threads.
Double lead threads. Explain that for our listener. What does that mean?
Okay, so imagine two separate threads starting side by side on the shank of the screw. For every single 360-degree turn of the screw, it advances forward twice as far as a single thread screw would.
Ah, so it drives in twice as fast.
It drastically increases installation speed. You can drive the screw in literally half the time, which is essential in high-volume drywall installation where time is money. This allows for rapid, consistent attachment while maintaining excellent holding power.
But if you take that same coarse double-lead screw and try to use it on a thin metal stud, you're going to ruin the connection, aren't you?
Instantly. You will have a total failure. The coarse thread would tear up the thin metal, we're talking light gauge steel studs, usually between 0.5 millimeter and 0.8 millimeters thick, and it would strip the hole immediately.
So no grip.
No grip at all. That's why you have to switch to the fine thread drywall screw.
The fine thread, that's the one with the dense, shallower threads.
Yes. The fine thread has threads that are much closer together and shallower in profile. This design is engineered specifically to self-tap securely into that light gauge steel. The denser threads ensure maximum thread engagement across the thin metal surface, creating a secure hold without ripping the material.
So it's a trade-off.
It is. If you use fine threads on wood, they tend to spin out and lack the deep grip required. If you use coarse threads on steel, they strip. The distinction is absolutely non-negotiable.
And finally, the point of the standard drywall screw is just a simple, very sharp needle point. It relies on sheer sharpness to pierce the paper and the substrate.
Yeah, a simple sharp point allows for rapid piercing of the drywall and the stud material with minimal drilling resistance, again, all in the service of speed of installation. But we also have to acknowledge the high performance variants, which link this product to the industrial tech screw family, the self-drilling or drill tail drywall screw.
And this is for heavier commercial construction, right? Not your typical home DIY.
Exactly. If you move into heavier gauge structural metal studs, say 1.5 millimeters or thicker, a simple sharp point just won't penetrate efficiently. You need the drill tail.
So I have a tiny drill bit on the end?
It's manufactured with a small drill bit built right into the tip. This tip first drills a pilot hole through the thick metal. The threads then engage the pre-drilled material perfectly. This dual function ensures a robust connection even when fastening to thick structural steel, maintaining the speed of installation required on large commercial sites.
We've established that the geometry of the drywall screw is surgical. It's incredibly precise. Now we need to talk about the material science that allows it to hold that shape and perform its aggressive tapping action. If a fine thread screw needs to pierce and self-tap into metal, the steel it's made from must be significantly harder than that metal. How do manufacturers achieve this level of performance in a tiny, mass-produced fastener?
It all comes down to the starting material and the subsequent heat treatment. The requirement is absolute. The screw must be harder than the material it's being driven into.
Oh, it's useless.
Completely. If the screw is too soft, the tip will dull, the threads will shear, or the head will twist off under torque. This requires specialized low-carbon steel, wire rod, and the intensive process of quenching and tempering, or Q&T.
Our sources clearly delineate the two major wire rod standards used in fasteners, C22 and C10B21. They sound nearly identical, but one small chemical addition makes all the difference in the final product.
They're cousins, really. Both are low-carbon steels, which means they contain less than about 0.25% carbon, which makes them highly suitable for cold heading.
And cold heading is that high-speed manufacturing process.
Yes, it's a high-speed, high-pressure process used to form the screw's head and shank without requiring heat. It's very efficient.
So C2022 is the standard workhorse, correct?
C2022 is the backbone of the general-purpose fastener market. It's highly ductile, easily formable in the cold-heading process, and very cost-effective. It's perfect for moderate-strength fasteners like our chipboard screw, where the material it's going into is less challenging. It provides the necessary basic strength after a mild hardening.
Now, C10B21, this is the high-performance material, and the B in the name stands for boron. How does adding just a few thousandths of a percent of boron transform this steel? This is truly fascinating microalloying.
This is where the magic of metallurgy really lies. The boron effect. Boron is added in incredibly tiny, almost trace amounts. Yet this minuscule addition drastically impacts the steel's hardenability.
Hardenability. Now, that doesn't mean maximum hardness, right? It's something different.
That's a key distinction. Hardenability refers not to the maximum hardness achievable, but to the depth and consistency of the hardness when the material is heat treated.
So when they heat treat a C10B21 screw, which is essential for those self-tapping fine threads, the strength penetrates deeper into the core of the screw.
Precisely. The boron acts to suppress the formation of soft microstructures during the initial rapid cooling, the quenching phase of heat treatment. This allows the manufacturer to achieve much higher and more consistent core hardness and strength. This is crucial for high-performance self-tapping fasteners, which demand a high-yield strength to prevent stripping and a high shear strength to resist the torque of installation.
So it's the key to making a strong self-tapper.
It is. C10B21 allows fasteners to reach performance levels equivalent to structural grades like Class 8.8, making it ideal for the demanding self-tapping task while remaining cost-effective compared to true alloy steels.
So it's the sweet spot. Maintaining the formability needed for mass production via cold heading, but achieving the strength required for performance through heat treatment. That leads us directly back to the quenching and tempering process. We summarized it earlier, but we need to understand the practical consequences if this Q&T process goes wrong.
Q&T is a balancing act. It's a trade-off between strength and toughness. If the process is controlled perfectly, you get a screw that is hard enough to pierce, but flexible enough not to break.
Okay, so what happens if the manufacturer fails during the quenching stage, the rapid cooling?
If the quenching is inadequate, maybe the cooling medium is too warm or the time is too short, the steel won't fully transform into hard martensite. This results in an underquenched screw that is too soft.
And in the field, what does that mean for the installer?
It means the tip will dull instantly when it hits the stud, the threads will deform or strip out the hole as they engage, and the screw will ultimately fail to hold the required load. It's a complete failure.
And what about tempering? That's the reheating part where they restore the ductility, right?
Yes. Tempering is the critical final step where internal stresses are relieved. If the screw is under-tempered, it remains martensitic and dangerously brittle.
So it's too hard.
Way too hard. You'll be driving it in perfectly, you apply the final bit of torque to set it, and the head will just snap clean off, often leaving the shank embedded in the stud, a catastrophic, frustrating failure that requires drilling out.
Right. And conversely, if they overheat it or leave it in the oven too long, an over-tempered screw.
Then you've ruined all the initial hardness you achieved. An over-tempered screw will be too soft and will fail in exactly the same way as an underquenched screw, dulling the tip, stripping the threads, and potentially shearing the shaft under load. Manufacturers have to dial in that Q&T curve with incredible precision, often monitoring the hardness in both the surface layer for cutting and the core for structural strength to ensure consistency across millions of units.
This precise heat treatment, especially when you're using high-performance steels like C10B21, brings us to a major safety concern that every reputable manufacturer has to mitigate: the silent killer known as hydrogen embrittlement.
This is a crucial risk, particularly when dealing with fasteners that have been quenched and tempered to high hardness levels. We're talking typically anything above Rockwell C35, which includes high-performance drywall screws and especially structural bolts like Class 10.9.
Okay.
These highly stressed microstructures are extremely susceptible to catastrophic brittle failure if atomic hydrogen is present.
And that hydrogen gets into the steel during the finishing process, specifically electroplating, is that right?
Exactly. When the screws are electroplated, for example, during zinc plating, the chemical reaction in the plating bath generates hydrogen atoms. These atoms are so small they can easily permeate the microstructure of the highly stressed steel. They then migrate to areas of high stress, like the root of the thread, and they accumulate.
And they don't cause immediate failure.
No, and that's the scary part. They initiate microscopic cracks that propagate over time.
So a screw can be sitting there, perfectly installed for 6 months, a year, and then just snap under a low static load. That's the definition of terrifying.
Yeah.
That is precisely why it's called the silent killer. The failure is sudden, brittle, and often occurs long after installation under normal operating stress. It is a critical concern for any high-strength fastener, regardless of its size.
So what is the non-negotiable step that manufacturers must take to eliminate this risk?
The solution is a mandatory hydrogen bake, or de-embrittlement bake. Immediately following the electroplating process, the fasteners are heated at a relatively low temperature, typically between 190 and 230 degrees Celsius, and they're held there for a minimum of several hours.
And that drives the hydrogen out.
It does. This thermal treatment is designed to increase the mobility of the absorbed hydrogen atoms, allowing them to diffuse out of the steel before they can cause internal damage. This quality control step is absolutely non-negotiable for ensuring the long-term structural integrity of high-strength components.
So we have a perfectly shaped screw, manufactured from boron-enhanced steel, meticulously heat-treated to ensure maximum performance and minimal risk of snapping. Now we arrive at the surface finish. Most of our listeners are familiar with the standard black color of the coarse thread drywall screw. Why black when everything else in the fastener world seems to be bright, shiny zinc?
This black finish is the ultimate illustration of specialized optimization. That is typically a black phosphate coating. And its purpose, contrary to what you might assume for a piece of metal, is not primarily corrosion protection.
Really?
No, it is a chemical compatibility finish.
Wait, so I assumed it was just a cheap way to get some corrosion resistance. But you're saying it offers minimal resistance, yet it's the standard.
Yeah.
Why sacrifice protection?
Because the drywall screw is designed for what's called a C1 environment, a very benign, dry, indoor setting. In that environment, maximum corrosion resistance is, well, it's irrelevant. What is relevant is how the screw interacts with the plaster finish. The phosphate process leaves a slightly rough, porous texture on the surface of the steel.
And that texture is the key for the finishing compound, the plaster.
Absolutely. The roughness is crucial because it gives the jointing compound a mechanical key, allowing it to adhere extremely well. More importantly, the black phosphate coating acts as a neutral barrier. Gypsum plaster often contains additives that, when mixed with water and allowed to cure against a thin zinc coating, can chemically react over time.
Ah, so zinc plating, while it's protective against rust, could actually interact with the plaster.
Precisely. In certain conditions, that reaction can lead to visible discoloration or ghosting of the screw head through the final paint finish, maybe years later. The black phosphate coating prevents this chemical interaction, ensuring the screw head remains permanently concealed and the wall finish stays pristine. It prioritizes aesthetic permanence and plaster adhesion over external durability.
That is a brilliant design insight. It's an environmental trade-off. However, we did note that the fine thread drywall screws, the ones designed for metal studs, are often shiny, meaning they are zinc-plated. Why the shift for the metal stud application?
The fine thread screws, being destined for thin steel studs, often benefit from the slight lubricity and anti-galling properties of the thin zinc plating.
Okay.
Zinc offers mild corrosion resistance, which is still perfectly suitable for the dry interior environment. Since fine thread screws are driven into metal, where the aesthetic interaction with the jointing compound is slightly less demanding, and the use case is often high-volume commercial work, where materials are standardized zinc plating is often deemed acceptable.
But you can still get them in black.
Oh, yes. You will still find black phosphate fine thread screws available, especially where the manufacturer wants total assurance against any chemical reaction with the plaster.
Let's ground this whole corrosion context using the official standards. The ISO 125-4 corrosion classification system. We're talking about indoor climate control spaces, which puts us right at the bottom of the scale.
We are squarely in the C1 category, very low corrosivity. C1 environments are defined as heated buildings with clean air, like offices, schools, museums, and residential homes where condensation is not expected. In a C1 environment, our sources confirm that the corrosion rate is negligible.
So you barely need any protection.
Basically, a thin layer of electro-galvanized zinc plating is adequate, and in some completely dry, non-condensing areas, even untreated or self-color, fasteners might suffice if aesthetic appearance is not a factor.
So the use of black phosphate is not a weakness. It's a confident decision based on the non-corrosive C1 environment, allowing the designers to focus on the more critical factor, plaster adhesion.
Exactly. It's a perfect example of engineering economy. Why pay for C4 or C5 corrosion resistance when your product is going to be buried behind plaster in a heated home? The cost savings are immense, and the performance in terms of wall finish stability is superior because of the specific chemical properties of the phosphate.
This leads us to the regulatory imperative. This is the European market, and these fasteners are structural components in a wall system. Compliance with the Construction Products Regulation, the CPR, and EN 14566 is mandatory.
The CPR dictates that construction products must be fit for their declared use. For drywall fasteners, that is defined by EN 14566. This standard goes far beyond simple dimensions. It ensures the screw interacts safely with the entire wall assembly, especially regarding safety requirements like fire resistance.
What are the specific performance tests mandated by EN 14566 that ensure quality? It's more than just a visible check, right? I mean, they're not just looking at it.
Oh, absolutely not. Compliance requires manufacturers to submit evidence based on rigorous testing. Key tests would include, first, pull-out resistance testing.
Okay, what's that?
This measures the force required to pull the fastener straight out of the installed gypsum board and start assembly. This is vital for ensuring the screw can handle the perpendicular load of the board itself.
Makes sense.
Then there's shear strength testing. This measures the force required to cut the screw in half when the board shifts laterally against the stud. This ensures the wall structure retains integrity during minor building movement or even seismic events.
Right, and corrosion.
Corrosion resistance, yes. Even though we know they're for C1 environments, the standard verifies they meet a minimum benchmark, usually via a salt spray test, to guarantee that the finish, be it zinc or phosphate, offers sufficient protection for non-aggressive indoor atmospheres.
And the big one. Fire.
Fire performance. This is critical. The screw must be tested as part of the total plasterboard system to ensure it doesn't fail prematurely under high heat, maintaining the fire separation integrity of the wall assembly for the required duration.
That explains why the CE marking is so important. It's a stamp that says the manufacturer has done all that complex testing and guarantees that the screw, as installed, contributes reliably to the building's overall performance, particularly for safety features like fire rating.
That CE marking, supported by a detailed declaration of performance, or a DOPO, is the buyer's assurance that the product is not just cheap hardware, but a tested component meeting the strictest EU health and safety requirements. If you're buying plasterboard screws in Europe, those markings are essential.
What an incredible deep dive into a product most people, I think, just completely overlook. The humble drywall screw turns out to be a brilliant piece of engineering tailored specifically for one of construction's most ubiquitous yet fragile materials.
The key takeaways for the informed learner are clear. Recognize that bugle head as the non-negotiable feature for paper retention and a flawless finish. And understand that the selection of threads coarse for fibrous wood, fine for light gauge steel, reflects an absolute tailoring to the substrate.
And realizing that the simple color change tells a whole story of chemical compatibility. The minimal corrosion protection of black phosphate is entirely intentional and sufficient because its true priority is preventing discoloration and ensuring superb adhesion of the jointing compound in a benign indoor environment.
But the most profound insight, for me, remains the metallurgy. The reliability of these self-tapping fasteners hinges entirely on the difference between the standard C1022 wire rod and the high-performance C10B21.
That tiny addition of boron.
That tiny addition of boron dictates the entire strength potential through the crucial quenching and tempering process, enabling the screw to achieve the necessary hardness without snapping.
And that very process of achieving high strength via Q&T is what introduces the severe safety risk we discussed, hydrogen embrittlement, especially when the fasteners are plated. That mandatory hydrogen bake is what saves critical structural connections from catastrophic delayed failure.
Which brings us back to our final provocative thought for you to chew on, extending the knowledge we gained about C10B21 and high-strength fasteners. We know high-strength, plated structural bolts like class 10.9 and above must be de-embrittled via baking. So, considering the critical safety risk of sudden brittle failure from hydrogen absorption during plating, what unexpected common DIY application or outdoor high-stress assembly might require you to deliberately choose a non-plated, or at least a non-electroplated fastener, even if it rusts faster on the surface, purely to guarantee the long-term, high-consequence structural integrity of that joint? Think about where failure simply cannot be tolerated.